Let's take a look at this image again, and can you tell us, what are we looking at? It looks like a Krispy Kreme donut.
I definitely went out and got a donut at the end of the day last Wednesday because I was so excited that we had a space donut to look at. Or maybe it looks like maybe a cat's eye or the eye of Sauron. But really what we're seeing here is the black hole's the shadow of its event horizon in the center and hot gas whipping around that black hole at speeds close to the speed of light. And that is bending space-time around it, causing all that stuff that's whipping around it to eventually fall inside the black hole.
Okay, that's kind of complex, I know, but we've got a demo to demonstrate how a black hole works. So let's get our demo up here. And those of you in the audience, you can watch on these screens. Will be the best place to see this.
All right.
So what are we looking at here?
Yeah. So here we have a piece of fabric. This fabric represents space and time. The fabric of space-time is what we're all in right now, and it's all around us. It's three-dimensional. Here it's 2D though, so we can do the demonstration a little bit better. Now, things that are in space and time generally have mass. That's the stuff that makes us up. We're made out of mass, this floor is made out of mass, everything around us, and things in space.
So here's an example of one thing that has mass, the moon. So anything that has mass is going to interact with the fabric of space-time. So let's see what the impact of something without too much mass has on our model of space-time. See how it's denting space-time just a little bit. It's bending it. Everything with mass bends space, including you. You're bending space just a tiny, tiny, tiny little bit. The moon is bending it, not even enough for us to measure.
However, we're not the biggest things in the universe, no matter how much we want to think we are. There's much bigger things out there, like stars, galaxies made up of stars, and at the center of some galaxies, supermassive black holes. Now, supermassive black holes are small objects that have so much mass and are so dense that they can bend space-time around them in a way that anything that gets close doesn't escape. Let's take a look at what that would look like. So I'm going to take this big object right here that's very massive, and I'm going to put it in space-time, and we're going to see what happens.
Whoa.
What happened to space and time?
It got a lot heavier.
Yeah.
And it just bent.
Yeah. So you can see that space and time is bending towards this massive object. And if this were in 3 dimensions, we'd see that bending in all directions. So imagine something is traveling near this massive object, like a black hole, like a piece of light. And I'm going to try to send it your way so that you can see it. Let's find out what happens. What happened?
It didn't make it too far.
Can I try it again?
Yeah, sure. Oh.
Almost? Nope.
That was an interesting orbit.
So it still didn't make it anywhere close to you. Because black holes and massive objects like black holes are so heavy, they have so much mass, their gravitational pull can pull everything towards them, even light itself. So from our perspective, it looks like the light gets sucked right into the black hole.
Okay,
Which
so
is why they're black.
Go ahead. What?
That's why they're black, because not even light can escape the event horizon of a black hole.
Now you talk about how big this black hole is, right? And the photo that our donut photo that we have, that doesn't look very large.
Well, let's take a look at it. So the photo of that black hole, and I'll take away our demonstration here, that photo of a black hole that we're seeing a small black hole at the center of it called a singularity. That's where all that mass is densely packed. And it's interacting with the space around it, and that space where it starts interacting with things is called the event horizon. So we're seeing the shadow of that event horizon right there in the center. All around it is stuff being pulled towards the black hole because of all that gravity from its mass. It's hot gas that's been ripped off of stars and planets heading towards this black hole, and is spinning, spinning, spinning around it, and it could eventually fall into the black hole itself.
How big is this? What's the size of this? What are we looking at here, this black hole?
Compared to us, it's huge. But compared to things that are out in the universe, not big at all. Take a look at this image. This is an approximate representation of how big this black hole might be compared to our solar system. You can see the sun in the center, Pluto's orbit around the sun, and Voyager, the farthest spacecraft we've ever sent away from Earth, out near the edge. So that means that the center of this black hole, that shadow, is bigger than our entire solar system and farther out than Voyager. But compared to other things in our universe, That's actually pretty small.
That's pretty small. Okay, it fit our solar system in, but it's pretty small.
Yeah.
All right. Now I get that the light bends, right? But why does it look fuzzy?
Right. So, like Becca was saying, that we're looking at something that's so enormously far away, and on the scale of galaxies, solar systems are really tiny. And so we're trying to see something which is stupendously far away and stupendously small. And in order to see that, even our best efforts are still yielding a fuzzy image. Now, if we were to see it from up close, we would be able to see more detail. But being able to see it at all is an enormous accomplishment that required a global cooperation.
So can we take a look at the spinning? We have a video
Definitely.
here. So tell us what's going on here, because this looks sharper
Definitely.
than the image.
If we were to be up close, we might get a little higher resolution or a bigger telescope. So this is a model, a simulation done by scientists on the team of what that kind of would look like, and also from different perspectives. That black hole in the center is so massive that it bends the light around it. So what you're seeing as we change our perspective with the black hole in this video is we see that light being bent around it as well. So we'd be able to see all of those dynamics if we had a little bit better resolution, a little bit, or we were closer, but we can still get all of that information from the image that was taken last week as well.
Okay, so explain to us what the Event Horizon Telescope is, because I understand it's not just one.
Right. So, in order to accomplish this incredible feat, in order to be able to see something so incredibly far away and very small, you need a telescope as big as the Earth, which is the Event Horizon Telescope. Now, we don't actually have a single telescope as big as the Earth. That would be really expensive, and it would probably be hard to keep working without breaking under its own weight, for example. So in order to get around that, what the Event Horizon team has done is gather together telescopes all around the world that are acting together. They are simultaneously observing black holes like the one at the center of the galaxy M87, and they're working together to effectively make a single telescope as big as the Earth with holes in it. So that means that they still have some work to do with this data in order to get a good image out of it. But it's basically as big as the Earth.
So Genevieve, I want to ask you, because you spent some time with telescopes in Chile. So were they involved in this program as well? And what can you tell us about the telescopes that you saw when you were there?
Right, so there are multiple telescopes around the world involved in this, in places like Hawaii, the United States, Europe, even Antarctica. And one of those sites was Chile. And the ALMA telescope in Chile is kind of an example of how the Event Horizon Telescope works, but on a smaller scale. Because with ALMA, you have a group of radio antennas on this high, dry, dark location in Chile that act together. When they're looking at an object at the same time, their data is put in the same place and synchronized so that they effectively act as a single larger telescope, which is also on a much bigger scale how the Event Horizon Telescope works.
Now with Event Horizon, all these telescopes you've got working all at once, are they taking photos at different times? I mean, how is this working?
Great question. They definitely need to synchronize. So these telescopes had to be taking a picture of the sky at the exact same time. Now, it wasn't just a little snapshot like you take on your iPhone. This was a long observation done by these telescopes all over the world, but very synchronized at the same time. Then all of that data was collected, and it was so much data that they actually couldn't send it via email to the people they were collaborating with. So they actually had to take big data drives and carry those around physically to be able to then bring the data together to get this picture.
Now, I'm going to ask you more about the data in a second, but what I do want to know is, do you guys know how they synchronize those telescopes?
How they synchronize those telescopes? I mean, they're definitely communicating with each other and using the satellites that we have that are globally connected to be able to synchronize their watches exactly and their algorithms and everything that they're using to collect this data.
Even using atomic clocks.
Yes, exactly.
Atomic clocks, okay.
Yeah.
Okay.
Yeah.
Now, I have some fun facts on this data, and we'll go back to the other photo in a second. This was 5 petabytes of data, which would be a half a ton of hard drives, 5,000 years of MP3 files, and a selfie collection for a lifetime for 40,000 people. Yeah. Do you want to tell us a little bit about this photo and what we're looking at here?
So what we're seeing here is Katie Bowman, a member of the Event Horizon team. She's an electrical engineer and computer scientist. These discoveries take a lot more than just astronomers. You need engineers, you need data scientists, you need educators who can help people understand the results, you need theorists. People from all different branches need to work together in order for us to understand these results. And so what she has here is all of the data from the different telescopes finally brought together in the same place. Funny note, one of the telescopes was in Antarctica, and the observation was taken in April, which is when winter was beginning there. So they couldn't bring all the data together until about 7 months later when the weather was okay in Antarctica to fly it out. So she's got it all together, and she led the team to write the software to start putting this data together so they could start making an image out of it.
Okay, so how do we collect this light? I mean, is there, you said there wasn't just one big telescope. I guess there's a reason for that?
Totally. So there's the reason we're collecting all this data is because we're using radio telescopes. They're collecting the longest wavelength of light, and it's like collecting rainwater. Instead of light, let's imagine it as water in a bucket. So if we had a big bucket, it would cost a lot of money and be hard to fix. That's the bucket that's the size of the Earth, right? We'd love that, but it's really hard. So instead, using these large radio telescopes spread across the world, we can make them like a lot of little buckets collecting rainwater at the same time. They're not going to collect all the rainwater, but by spreading them out, they're going to collect different types of rainwater from different areas and learn different things about the rainwater that's falling, or in this case, the light. Then when you bring all that information together, you can correlate it or layer it on top of each other to get a broader picture of the entire thing that you're looking at. In our analogy, it would be rain, but in this case, it's that radio light that we're looking at in the middle of this galaxy so far away.
Can you tell us a little bit about what radio light is as opposed to like the lights we're sitting under?
So when you hear radio, you think, oh, well, you turn on the car radio and you hear it, right? That's sound. But radio is actually not sound. Radio waves are a form of light. They're just much too red for our eyes to see. Our eyes only see the rainbow of light, but there's light beyond red, which is called infrared, and beyond that is radio. And so these long wavelength forms of light, these low energy kinds of light, are great ways to probe things like what's happening down in the hearts of galaxies, because that light is able to get through all that gas in between us really well.
Okay, so why did we know to look at this galaxy and not another one for this black hole?
So in this case, that's a great question. How would we know to point this giant telescope at this one particular spot on the sky? Now, this is down in the heart of a giant galaxy called M87, an elliptical galaxy with billions of stars in it. But this galaxy has a special trick up its sleeve. What we see here is a Hubble image, but layered onto that Hubble image is a radio image showing a jet. We're going to see a close-up of the part of the galaxy that has the jet shooting out of it here. And so that jet is a narrow, focused beam of particles zipping out of the center of the galaxy, much more focused than a laser pointer and stretching about 5,000 light years in length. Now, what could cause these particles to be moving close to the speed of light, all in the same direction and emitting light as they're going the way that we observe it? The only thing that theorists could think of to explain what we are observing here is a giant black hole with a swirling accretion disk around it, which is powering that jet. So we had a really good indication that there was a supermassive black hole in the center of M87. We didn't have a picture of it, but we had really good evidence of it before the Event Horizon looked at it.
Do you want to tell us what an accretion disk is? And can you point it out on this image and so that we can
Yeah, if we look at an image of a black hole, an accretion disk can actually occur around any massive object that has stuff spinning around it. In the case of the black hole, the accretion disk that we're seeing is shining with that light because it is hot. It's very, very hot. So much so that it's plasma. It's kind of, some people call it the fourth state of matter. So it's really, really hot, and it's shining bright, and it's swirling around that black hole, spinning around it in a flat disk. So that's why we call it the accretion disk, because it accretes or gathers around it, and then it's spinning around it as well.
How far away is this from us?
The whole galaxy is about 54 million light years away. That means that the light we're getting from it now is 54 million years old.
Is the black hole still there?
Probably, yeah. Probably. On the scale of galaxies, 55 million years isn't a very long time. For example, our solar system has been around for about 4.5 billion years. And our solar, and who knows what was before that and what will come after. So this black hole is probably still there. It might not look the same as this image that we're taking here, but we have pretty good evidence that it's probably still going strong.
Yeah, we have a lot of people in the audience today, and I'm sure they're interested. If they go outside this evening, where would they look in the sky generally to where this galaxy is in this black hole?
So in order to find this galaxy, you'll have to look at the constellation Virgo. And Virgo will rise a little later tonight. So you'll have to wait until well after dark in order to do this tonight. A lot of people can recognize the Big Dipper in the sky. And so look for that pattern of 4 stars in kind of a square and then 3 stars in a curved handle in the sky. That'll be your tool for finding this part of the sky. It's really useful for finding other things too. So that curved handle will arc to the bright star Arcturus and then just keep going and spike down to the bright star Spica, which is in the constellation Virgo. That'll get you in the right part of the sky for seeing this galaxy.
Okay, so black holes for a long time were a theory, and part of the theory is time travel. So will black holes allow us to travel through time?
So time and space are inextricably linked. Space-time is one entity in our universe. And what we see when we look at the black hole is we're seeing relativistic effects, which is what you get when things are moving close to the speed of light. And all sorts of weird things that start to happen to both space and time. The way that light is bent around the black hole is very weird and very cool. And it also has effects on time. For example, if you fell into the black hole and I was watching you and you were like shining a light back at me, as you got closer and closer to the black hole, aside from being in a very hot environment with lots of radiation and all sorts of, and being in space and everything, you wouldn't actually notice anything special necessarily as you cross the event horizon. But from my point of view, I would see you move slower and slower, and the light from you would get redder and redder. So it's a kind of a way of time travel when you get close to these very strong gravity fields. But sometimes people also talk about wormholes. Are black holes wormholes? Now, wormholes are kind of a mathematical idea, and they might exist, but we don't know yet. What I can tell when I study the data from the black holes is that they get heavier over time. Like this giant one, this one in the center of M87, it weighs more than 6 billion times as much as the sun. You make a black hole when you collapse a star, but no star is that big. The only way it got that big was by swallowing other stars, gas clouds, other black holes, things like that, to get bigger over time. That mass is still there in whatever weird, twisted form we don't necessarily understand yet, but it hasn't gone anywhere else.
Becca,
What would happen if you put a human through a black hole?
we wouldn't know. We'd never get a signal back. We would probably never ever find out unless they found a way to get out of it or to signal back to us. But of course, we found out that nothing can escape it, even light. And the way we communicate is with light, with radio waves. So we probably wouldn't know anytime soon. So unfortunately, we're probably not going to go into any black holes, but studying them from afar can tell us a lot more about their physics and these relativistic effects, which can then help us theorize more of these ideas in the future.
I heard about spaghettification.
Oh, yes.
And so I could be really thin.
Yes, as you fall towards the black hole, from our perspective, it'll look like you've strung out into like literally your atoms, the smallest particle of you, and it'll look like you're a long line of spaghetti. So that is an actual scientific word, spaghettification.
That will be a word I remember. Why is this image so important?
So to me, a big part of why it's so important is, like, look at everyone who's here. We think black holes are cool. Black holes really resonate with people. They're such a weird and marvelous phenomenon that people just like them. And so getting to see an actual picture of one for the first time ever is, I think, just by itself, really cool. I think everyone can kind of appreciate that. But it can also help us test our theories. So we have all these theories and simulations and artists' conceptions of what a black hole would look like, what's happening inside it, how does Einstein's relativity interact with, say, gravity and interact with quantum mechanics. But the